So another impact on conventional generators can actually be a loss of market share and low wholesale electricity prices. So let's look at an example from wholesale electricity markets. So remember that when renewable energy is integrated into wholesale electricity markets, there are a couple important characteristics that it has. And the first is that it has a very low variable cost of electricity. Remember, most of the cost of renewable energy, like wind and solar, are the capital cost. Once you build the solar farm or once you build the wind farm, the cost of producing the electricity is almost zero. Because of that extremely low variable cost of renewable energy, it is almost always taken by the market. We even used to call it, we have called it in previous lectures, demand reduction. And so what that means is that when wind or solar is sold into a competitive wholesale electricity market, it almost always displaces other more expensive and typically higher polluting types of generation. So renewables are way down. If we think about the system supply curve in a competitive wholesale electricity market, the traditional position in the system supply curve for renewables is way down at the bottom left. And so what that means is that if you're a coal plant and under normal conditions, you are to the left of the demand curve, which means that your market is taking your electricity. You're cheap enough to provide electricity. The intersection between supply and demand occurs to the right. And so you're able to sell your electricity and you're able to sell it at the market clearing price. But what happens if there's an explosion in growth in renewable energy? And so greater renewables would then push the system supply curve out to the right. And now all of a sudden that coal plant is a little bit to the right of the demand curve, which means it's effectively too expensive in order to sell its electricity. The market doesn't need it anymore because there's now so much renewable in the system. And so in this case, we might see that the coal plant is losing market share. So it's not able to sell as much electricity anymore now that there's a greater portion of renewables in the market. At the same time, because those renewables are pushing the system supply curve out to the right, the intersection between supply and demand now occurs at a lower point on the y-axis, which means that the plants that are selected to run get a lower price for electricity. So in recent years, deregulated markets have been experiencing low wholesale electricity prices, and we've talked about this before as something that has helped drive nuclear power out of the market, even though nuclear power is essentially a zero carbon source of electricity. The existing plants that we have not been able to survive in competitive markets for electricity. And part of that is due to a slowdown in electricity demand growth. A huge part of that has been to low natural gas prices. And then a third important part of that has been due to rapid growth in renewable energy, which have been pushing wholesale electricity prices down in the manner that I just described. Now, just to be clear, when we talk about thermal electric power plants, especially coal and natural gas, losing market share, that also means lower emissions. So it's not all bad. The third impact that increased renewable energy can have on electric power systems is actually by impacting other renewable energy providers. And it does so by lowering electricity prices and forcing system operators to curtail wind and solar because of a temporary overabundance in renewable energy. So another growing problem that we see, particularly in systems that are all in on renewable energy that are developing very quickly, is a situation called generation oversupply. And so this is when there's too much renewable energy generation in the same place at the same time. So how can this happen exactly? So one big part of this is that you might have periods of the year or periods of the day when demand happens to be particularly low. Right? That could be during a period of the day where it's not too hot or it's not too cold, or it could be a particular time of the day or the year where economic activity is low, where people are just using less electricity. At the same time, if you have low electricity demand that overlaps in time with a period when you have a lot of renewable energy available and that system supply curve shifts way out to the right, now what you get is a situation where the intersection between supply and demand occurs at a point on the y-axis that is extremely close to zero, which essentially means that almost all the demand in the system can be met by renewable energy like wind and solar. So, in a situation like that, if you have an excess of wind and solar, in fact, if you have too much wind and solar, so the supply of electricity is greater than the demand for electricity at some point in the grid, that electricity needs to go somewhere else because electricity demand and supply always have to be balanced. So, if there are constraints on the transmission system that prohibit that electricity from being sent out, for example, then you can get locations within the grid that experience oversupply. And we've seen an example of this before, just in this same lecture, right? I showed this to you before as an example of where in the part of the map labeled A, where you have negative electricity prices, which indicates an overabundance of renewable energy. Those providers actually would like to send electricity to the area labeled B that's experiencing higher electricity prices. But because we see this color gradient, right, what that indicates is that there's no physical transmission to get electricity from point A to point B, and that can happen. So if surplus electricity cannot be exported to another area, for example, due to transmission constraints, then some generation has to be forcibly curtailed, and that can include variable renewable energy. And so what this figure shows is forcible curtailment of variable renewable energy in California through time. And what you see is that especially during low demand periods of the year, which would be April, May, March, that also have a lot of hydropower because of water availability, and might also have a high amount of wind and solar, you're experiencing more frequent periods and more severe periods where there is just too much renewable energy on the grid in California, and increasingly some of that energy is being curtailed or forcibly turned off. Now, when this happens, wholesale electricity prices in markets can actually go negative. So, how can wholesale electricity prices actually go negative? We're talking about the intersection of supply and demand. How can that ever happen at below zero on the y-axis? So it's a little complicated, but the reason is that many renewable energy producers still get tax credits from the U.S. federal government for every unit of energy they produce. So if a wind farm gets a tax credit from the U.S. federal government such that it earns $20 per megawatt hour just as a tax credit, in theory, it would be willing to sell electricity at any price in the market greater than negative $20 per megawatt hour. For example, if it was selling electricity for negative $15 per megawatt hour, it would still get $5 per megawatt hour profit because of the $20 per megawatt hour tax credit. So if you are in a situation where the whole market is flooded by renewable energy, who is competing against who? It's actually renewable energy producers competing against other renewable energy producers. And the only way to do that, since everybody's marginal cost is zero, is actually to sell at a negative price. So the renewable energy providers that have big tax credits are able to sell at a lower price while still making a profit. So what does that actually mean for buyers and sellers of electricity? Well, it creates a very strange situation where customers or consumers of electricity on the wholesale market are paid for every megawatt hour they buy from the market. And generators of electricity are charged for every megawatt hour of electricity they sell into the market. So think about this, who in theory could make a lot of money taking advantage of this? Who would be in a good situation to buy electricity when the price is negative and sell electricity when the price is positive? So the answer is cost-effective grid-scale energy storage. In other words, the holy grail of incorporating lots of renewable into the grid. And so we'll talk more about battery storage in a later lecture. But that's why we see here that battery storage is really an integral piece to grids of the future that may be significantly more reliant on variable renewable energy. We need devices that can actually store electricity when that variable renewable energy is overabundant and not worth as much, and then discharge it later when wind and solar are not as available and when the price of electricity is much higher. Another solution would be more transmission capacity. We sort of alluded to this earlier in the lecture. If there's one part of the grid that is experiencing oversupply in variable renewable energy, and then there's another part of the grid that it's experiencing a shortage, then connecting those two regions physically via high voltage transmission capacity would allow the area that has too much wind and solar to send that electricity to the area that has not enough wind and solar. And we have some actual evidence that building new transmission capacity helps reduce the frequency and magnitude of oversupply events and negative pricing and curtailment of variable renewable energy. And so that's what this figure shows. The blue lines show estimated hourly curtailments of electricity of wind power in the ERCOT or Texas wholesale market. And green show the negative electricity prices in that same market. And what this shows is a gradual decrease in the frequency and magnitude of curtailment events and oversupply events. And this was caused by an investment in additional transmission capacity. However, increasing transmission capacity, especially over large distances, is very difficult. It's extremely expensive. There's a lot of not in my backyard mentality where people don't want to live next to high voltage transmission capacity. There can be environmental impacts, and there's a question of who's going to pay for it. So for all of these reasons, a lot of projects that have aimed to develop transmission to deliver large amounts of variable renewable energy from one place to another have failed. Interestingly, in the long run, the impacts of renewable energy on electricity markets may primarily affect renewable energy developers themselves. For example, solar is much more limited to a single period of the day. And what that means is that adding more and more solar only helps during the period when the sun is shining. And we can see that from the duck curve, right? So if we look at these different colors of the lines, which represent different years, as the state of California is adding more and more solar to the grid, it's only decreasing demand during this one period of the day. And so what that means is that it's only decreasing electricity prices during this one period of the day. And if you're a generator that can only produce during that one period of the day, in other words, a solar farm, then adding more solar actually decreases the price and the value of solar. And so that's what this figure shows. So this shows in red the decrease in the average market price for electricity as a function of solar PV penetration in a grid. And so that's the average market price over the entire day. The blue represents the average electricity price experienced by solar farms as a function of solar PV penetration. And so what we see is that disproportionately adding solar to the grid decreases the price for solar providers, not necessarily other participants in the market. And so what this is essentially saying is that in a competitive market where the price is responsive to fluctuating supply and demand, solar is sort of eating its own lunch. As you add more solar, the value of solar declines. And so in the long run, what that does is without any sort of support, it reduces the investment value of solar capacity because if we're thinking about doing a net present value estimation of the long-term, discounted cash flows, profitability of the solar farm, or trying to give a projected, a solar farm that we might be wanting to build a score in terms of its economic viability. And a big part of that would be how much revenues the solar farm is making on a year-to-year basis. So profits are revenues minus costs, and revenues for a solar farm is how much electricity they produce times how much they can sell that electricity for. So prices really matter here. So if adding more and more solar drives the price of electricity for solar farms lower and lower, that is going to impact the investment value of solar farms. systems. Okay, so that's all for this lecture. Next time we're going to talk about energy storage and demand response. So reading number 9 is posted.